Okay, so this is the third and final talk about hierarchical hyperbolic spaces. It's also the first one where I'll use those words. So if you missed the first two, then you missed some sort of motivation, but I'll kind of re-explain everything that was discussed in sort of an abbreviated form in the first two talks, or at least discuss some of the things. So the title of the talk is Quasi-Flats in Hierarchically Hyperbolic Spaces, which I'll abbreviate HHS. And everything I'll say today is joint with Mark Hagen and Alessandro Sisto, who tried to get me to change my first name to start with an H, but maybe it's the fourth letter in my name or the third letter, whatever it is. Okay, so let me start, before I tell you what a hierarchical hyperbolic space is, let me start with telling you what the motivating question, or what, at least for this talk, will be sort of a motivating question for what I want to talk about. So here's a motivating question. Well, let me actually say this is a motivating theorem. Motivating. Which is sort of the background for what this talk is. So the motivating theorem is due to Eskin-Farb and Kleiner-Leeb. And says the following thing. It says, suppose that we want to understand a symmetric space of non-compact type. So let's let X be a symmetric space of non-compact type and of rank n greater than or equal to 2. Okay, and then let's consider, let's let phi be a from Rn to X be a Kc quasi-isometric embedding. Okay, so another word for a Kc quasi-isometric embedding of Rn into your space is a quasi-flat. So this is a quasi-flat. So let phi be some fixed quasi-isometric embedding into my space X. The theorem then says, then there exists a constant f, which just depends on k, depends on the multiplicative constant of the quasi-isometry, so that the image under phi of this flat, this quasi-flat, lies within a bounded neighborhood of a bounded number of flats. Then there exists a constant f of k such that phi of Rn is contained in a bounded neighborhood of at most f of k flats. Okay, so this is the sort of prototype for what's called a quasi-flats theorem. So this theorem says if you have a quasi-symmetric embedding of Rn into your symmetric space, where the dimension of n is equal to the maximal rank of your symmetric space, so the maximal dimension of an isometrically embedded Euclidean space, then the entire image of that thing is the entire image of that quasi-flat is contained inside a uniformly bounded number of standard flats, some bounded neighborhood of a completely bounded number of a uniformly bounded number of flats. Okay, so this theorem actually has some precursors too. So this is Remark. So I said it in the higher. I said this in the higher rank case. So if n was equal to 1, then this is the familiar. Then this theorem also holds, and it's called the Morse lemma. well, if n equals 1 and x is hyperbolic space, then this is called the Morse lemma. It's often called the Morse lemma more generally. There, it's a theorem of Mostow's. And so, just to draw a picture, what does that mean? If you're in H2 and you take some quasi-flat, which a priori is kind of very messy, then it turns out that there's in the case n equals 1, this constant f is actually equal to 1, and there's some one-dimensional flat, which is just a geodesic, and the entire quasi-flat is inside this bounded neighborhood of, as I draw it, it doesn't look so small, but actually there's some kind of fixed tubular neighborhood of this geodesic that this entire quasi-flat lies inside. Okay, so Morse did this in the hyperbolic case, and then Mostow generalized it to symmetric spaces of rank 1 generally, and then these guys generalized it to all symmetric spaces. Okay, so the question in general then is to try to understand the question: what spaces have or satisfy a quasi-flats theorem? Quasi-flats theorem. So something like this, something where you have some notion of what a standard flat is, and every quasi-flat lies uniformly close to 1. And it's worth noting that in the symmetric space context, so Eskin-Farb wrote a short paper treating just the case of H2 cross H2, and that even in that sort of simple case, you don't get something as nice as in the rank 1 case. So you don't get in the rank 1 case, everything lies uniformly close to 1 flat, but in the general case, you may need multiple flats. Okay, so this is a general question. Let me just note in particular, there was a conjecture of Farb, Benson-Farb, where he said, he asked, or he conjectured that does the mapping class group satisfy such a theorem? So it turns out that the answer is yes, and all, that's what I want to talk about today. And in fact, there were a number of other questions about whether certain spaces satisfy quasi-flats theorems. And so the goal of my talk today will be to sort of reveal a way in which that's true. So I actually think of, I sort of structured these talks like an RK Narayan story, where in the first 2/3 we were introducing a bunch of interesting characters and telling interesting properties about them, and a priori there was sort of no relation between those characters, but they seemed to have something in common, and now I'll kind of reveal the common structure that sort of ties everything together. Okay, and so the way that we'll do that is by what I call hierarchy hyperbolic spaces. Hierarchy hyperbolic spaces. Okay, and so what I want to do is I'm not going to go through and sort of just list the axioms for these spaces, but what I want to do is kind of tell you what sort of the basic structure is that this consists of, and while I'll do that, I'll play two different games at the same time. So one is I'll name kind of structures in the general setup, and at the same time, I'll tell you about what the structure is in the case of the mapping class group, which if you were here for the first lecture, I sort of did in detail. But if not, you can sort of work it out from what I say, what I'm talking about. I'll give a little bit of indication, and then I'll explain what some other hierarchy hyperbolic spaces are. There should be a Y here. Okay, so the general setup has the following thing. So I'll start with some space which I'll call X, which will be a geodesic or a quasi-geodesic, say quasi-geodesic metric space. And in blue, let me just say a particular example, the mapping class group of S will be an example of a quasi-geodesic metric space that satisfies these axioms. Okay, so in addition to having our quasi-geodesic metric space, we'll also have another set, which I often call script S, which is our index set. Okay, and in the case of the mapping class group, which I'll draw in blue, this is the set of Y containing or equal to S. So these are, in other words, this is the set of subsurfaces of S. Okay, the set of all subsurfaces of S. And when I say subsurface, I mean non-trivial. I mean homotopy class of non-trivial, non-peripheral subsurface, essential subsurface. That's the word I was missing. Essential subsurface of S. Okay, so that's my index set, and then the last kind of general. Yeah, sure. So here's a surface, just a pi1 injective subsurface. It can have boundary. Yeah, that's right. It has to have boundary, otherwise there will be nothing. So yeah. So a pi1 injective, the homotopy class of this pi1 injective subsurface. Okay, so those are my set of subsurfaces, and then I'm going to have a collection of what I'll call C of Y. So this is going to be a set of spaces which are indexed by my index set, and that's why it's an index set. And so there's a set of these things, and each one of these is a geodesic, hyperbolic metric space. Okay, and this is the identical notation. Sort of in the general context, we use the identical notation that we do in the mapping class group context, but there I call these C of Y. And just to write that in words, these are the curve graphs associated to subsurfaces. So the curve graph of subsurfaces, of the subsurface Y. And you do that for every Y contained in or equal to S. Okay, so those are the three kind of types of spaces that we have involved. We have the metric space we're interested in, some index set, and then that index set index a bunch of delta hyperbolic spaces. And I should just say, since relative hyperbolic groups seem to be fairly popular in India, that there's a slight generalization of this structure, which we call a relatively higher hyperbolic space, where most of these things are hyperbolic, and in a way that I'll kind of explain in a second, there's sort of one class of them which is not hyperbolic. And if you do that, you can sort of recover the class of relatively hyperbolic spaces as a special case of this. So that's something to sort of keep in mind too if you're interested in that. Okay, so this is the structure. And now what we have now is some other ways that combine. We have ways of sort of matching one element of an index set to another. So let me write it like this. So here's the additional structure. S has. Let me say it in a minute. Let me put this down, and then I'll return to it. Yeah, I realize that maybe it was 5 minutes premature to have said that. So S has, or maybe 3 minutes. S has a partial order, okay, which we generally call nesting, and we usually denote by kind of a square containment sign. So there's some partial order called nesting on elements of S. And there's a few properties of this nesting. For instance, there exists a maximal element. So there exists a nest maximal element, which we normally just denote by a Roman S. So we have there's a script S, but this is just a normal S. And chains are bounded. Okay, and in the mapping, so in the mapping class group, setting, here just nesting is subgroup is subsurface inclusion. Subsurface inclusion. Okay, the maximal element is just the big subsurface S. So that's the maximal element, and the fact that chains are bounded is just because right, each one of these subsurfaces is sort of eating up some additional amount of pi1. You're filling up the subsurface, and so there's a finite depth to those chains. Okay, and so now to answer Mohan's question, to get the relatively hyperbolic setting, what you do is there's maximal elements. So since chains are bounded, there's also minimal elements. There's elements that don't have anything nested inside them. And to get the definition of a relatively hyperbolic space, of a relatively hierarchically hyperbolic space, is that every one of these spaces is hyperbolic, except for nest minimal ones where you don't have any hypothesis. Okay. All right. So we have nesting, and then there's another relation which we call, so S has an anti-symmetric, a anti-reflexive symmetric relation, which we call orthogonality. And we usually denote by this perpendicular sign. So it has this relation, some relation called orthogonality. And here, again, you have there's a maximal order to how many things can be pairwise orthogonal. So there exists a bound on the number of simultaneously pairwise orthogonal elements of, simultaneously pairwise orthogonal elements. Okay, and so people can probably guess what the right notion of orthogonality is. For the mapping class group, what is it? Yeah, exactly. So it's disjointness. So here, orthogonality is disjointness. Okay, and then we also get the bound on the maximal number of pairwise orthogonal elements, right? It's the complexity of the subsurface, right here. So the bound is 3g plus p minus 3. Okay, so sometimes this is called the complexity of the surface. Often this is denoted by C of S. Everyone has their own kind of way to write that without it looking anything like what a Greek might recognize as the letter. But anyways, so there's some bound to this. This is the complexity of the surface. So this is the complexity of S. Okay, so we have these two things, and then we have one more amount of structure, which is something that we spent a bunch of time talking about in the first lecture and another version of that in the second lecture, which is there's maps from your quasi-GS symmetric space to any one of these hyperbolic spaces. Okay, so there exist. Actually, maybe I should write this on the next board so I have enough space. Okay, so there exist coarse Lipschitz maps, which I'll write pi sub y, which map x to c of y for each y in my index set. So there's a bunch of coarse Lipschitz maps. And one more thing is these coarse Lipschitz maps, right? And they send. So really, they're not mapping to points, but I'm abusing notation there slightly, sending points to bounded diameter sets, uniformly bounded diameter sets. Okay, and in the case of the mapping class group, these are just what we called subsurface projections. Right, which meant that we had a way of thinking of the mapping class group as a collection of kind of curves on the surface, and this was essentially intersecting with the subsurface and then doing surgery so that you get a collection of simple closed curves. And that collection was bounded diameter. So these are the subsurface projections. Okay, so that's the general setup. There's a little bit more structure that I don't want to talk about, but these are the sort of key ideas. And then once you've set this up, there's a bunch of general theorems that hold. So here's a few general theorems. Yep. That's right. So I'll come back and I'll talk about it later. But yeah, this is something like the rank. Yeah. So that's why I did this example. This is the rank of the mapping class group, and it shows up as the rank in several contexts. So, and we'll see that more precisely in a little bit. I'll put up that definition. But for now, so there's a couple theorems. So one of which is the common generalization of these two statements that I made in the last two talks, which is there's a distance formula. So for each sufficiently large constant t greater than 0, there exist constants k and c such that for every pair of points in my space X, the distance in X between A and B can be kc quasi-asymmetrically estimated by summing over all y in this index set. And what do I sum? Right, I sum the distance in the curve in the graph, right, in this hyperbolic space associated to y of the projection to y of A and the projection to y of B. And again, everything was coarse, so this would be an infinite sum if you weren't careful. And so what you need to do is add these little curly braces and threshold at t. So you throw out all the distances less than this bound t, and when you've done that, it turns out that a posteriori, this is only a finite sum, even though it seems like it should be an infinite sum. Only finitely many terms are non-zero, and that uniformly estimates the distance between these pairs of points. Okay, so this recovers the mapping class group theorem. So we actually, in this general context, we prove this theorem, and we give like a very short elementary proof of what was the main theorem in Maser-Minsky's big paper, and then this also works in other cases. So that's one theorem. Another theorem, which sounds a little bit more technical, but I want to sort of use this theorem, so let me put it up. So another theorem, which I'll call this, so maybe this theorem has a name. This is the distance formula. And this theorem has a name, which is hierarchy paths exist. Okay, so hierarchy paths was a name that was used by Maser-Minsky to refer to a particular type of paths in the mapping class group, which I talked a little bit about in the first talk. So we have sort of a generalization of that works in this context, which is the following object. So for every AB in X, there exists a uniform quality quasi-geodesic gamma from A to B. Okay, so you have this metric space. There exists some nice uniform quality quasi-geodesics connecting any pair of points. And the particularly nice property about this uniform quality family of quasi-geodesics is they have nice projections. They behave nicely under this map. So there exists a uniform quality quasi-geodesic gamma from A to B, and moreover, for each element y, the map that you get, if you look at the path projection to y, to the curve complex of y, or I just wrote projection y, projection to y of gamma is an unparameterized quasi-geodesic. Okay, so unparameterized means, so it may stop for a long time, and we don't kind of control that, but it moves nicely through this delta hyperbolic space. So in the examples, when I talked about this for the mapping class group, I sort of talked about how there was these particularly nice paths, and as you followed along that path, it sort of just moved. At one time, it's always moving through some curve complex in a nice way, and then sort of freezing what's going, and then not doing anything in the other curve complexes, and then kind of moving through another one. But it never sort of goes backwards. You never have to move forward through some curve complex and then move back and then move forward. So this kind of these nicely move through all these different hyperbolic spaces at the same time. So uniform quality means the quasi-isometry constants depend only on x, not on a and b. Yes. Right. I could have said, given x, there exists k and c such that for each a, b. That's what I mean by uniform. Oh, and I didn't even write anything here, so I can go straight to this board. Okay, so those are that's the general setup, and those are two basic theorems. So there's a timer that I didn't notice until the end of my last talk. So okay, I have 44 minutes left. That's right. Yes. Yes. Yeah. Okay. So I wrote in blue what the mapping class group setup was. So the whole second lecture that I gave was talking about some structures on rags. So let me kind of, in 3 minutes maybe, just recapitulate that lecture in this language. So maybe I should use a different, well, I guess white's fine. I was going to use another color for the example, but let's just do it in white. So here's another example. So right-angled Artin groups. Right, so, yes, okay, so one of the axioms I didn't tell you is, okay, so everything is either nested or orthogonal, or if you're not nested or orthogonal, then we call those transverse, okay? And if you're transverse, right, so in the surface context, that corresponds to overlapping subsurfaces. In the transverse case, there's an assumption that you satisfy this, this axiom where the image into the product of those two spaces looks like one of these crosses. The thing that worked in the mapping class group that and worked, and we also talked about a little bit in the right-angled Artin group case. So there's a hypothesis there. There's also a hypothesis on what happens in the nesting case, which also sort of gives you a picture that roughly looks like this. So that's right. That's another axiom I didn't talk that I didn't mention, but there's an axiom that sort of explains that in that case you get a behavior like that, and that's what sort of ties together these various properties. That's right. So the point is that things that don't nest or orthogonal, they satisfy this Behrstock inequality, and then yeah, that's one of the axioms. And then there's another one that explains in their nest. If there's in the nesting case, you also get some control over what the image is into the product. Okay. So what happens in the rag case? In this case, right, a right-angled Artin group, there was some defining graph, and then you had some associated Cayley graph of a group, which we called A sub gamma. Okay, so here that's the geodesic metric space, the Cayley graph of A sub gamma, or actually, yeah, right, just the Cayley graph of A sub gamma. The index set, what did that consist of? So that consisted of, you looked at so gamma was some graph. Okay. Given some subgraph of gamma, you could look at the Artin group associated to that subgroup, okay? Or you could look at cosets of those. Those are the indices. The indices are cosets of sub-rags that you get by looking at a subset of the projection of the defining graph. So here's gamma. So S is equal to the set of G of A sub lambda, where lambda is contained in or equal to gamma as a subgraph, and G is an element of A of gamma. Okay, so for instance, if I pick this vertex, that's a subgraph of this form, and then I could look at left cosets of that. Those would be the elements in the index set. There's one place where we need to be careful, so it's really, the fine print here is it's this modulo some equivalence, where the equivalence is what we call parallelism, which just means if you have two cosets, G of A lambda and h of a lambda, which are a bounded distance apart, then they're equivalent. Okay, so it's just bounded Hausdorff distance between these cosets. So this is just bounded Hausdorff distance. Okay, so you have one representative of each parallelism class. Okay, and so then what else do we need to say? So there's a space, there's the index set, there's now some collection of delta hyperbolic spaces, right? So we know what that collection is, because we talked about them last time. So C of A sub, well, let me say this. So C of A sub gamma is just the Cayley graph of A sub gamma, but with respect to an infinite generating set. So first you put in the vertices of gamma, right? That would just be the normal generating set. But then you also put in union A of lambda for each lambda contained in S. Contained in gamma. Okay, so in other words, you cone off every one of these Artin subgraphs. And when you do this, you get an infinite diameter space. This was also called the contact graph. So the contact graph of the Salvetti complex of A sub gamma, but I'll just write of A sub gamma. So that's what you do for any particular Artin group. And then you can do the same construction for any one of the subgraphs, or for any one of the left cosets of the subgraph. It's just isometric to whatever the subgraph was. Okay, so then similarly for C of G of A lambda. Okay, and then there's my nesting, right? So nesting is again just subgraph inclusion. Subgraph inclusion, and orthogonality corresponds to whether or not those two, like up to parallelism, which I'll maybe brush under the rug, whether or not those two Artin subgraphs span a direct product. So inside the Cayley graph of A of gamma, do these two Artin subgroups span a direct product? So this is just spanning a direct product. In the fine print, if you care, is up to parallelism. Okay. So that's essentially a summary of what we did in the second talk, but in a more compact language. Okay, and so here's some examples of hierarchically hyperbolic spaces. So, right, we already did two examples. We did the mapping class group of S, and we did right-angled Artin groups. So something new, actually something I sort of talked about in the second talk already, was cat zero cube complexes. So cat zero cube complexes admitting a geometric action. Okay, so cubulated groups is another short way to say that. So that's a theorem. So Hagen, Sisto, and myself had proven this in a special case, but then the general case is due to Hagen and Tim Seuss. Okay, so that in particular, I should say, in particular, this includes all right-angled Artin groups. We had already shown that, and all I'll just abbreviate this right-angled Coxeter groups, if you know what that is. We're not going to talk about those much, so I'll just say that. But if you care about it, it includes those as examples. 4. Yeah, you need some bounded geometry. That's right. Yeah, you just need the right bounded geometry. Okay, so 4, right, to tie in a little bit with this morning's talk, Teichmuller space. And if I say Teichmuller space, right, everything here is a metric structure. Teichmuller space is a priori just some topological space, but there's different metrics we can put on it. And so I'll say Teichmuller space with both, or with either, with both the Teichmuller metric, with both the WP metric and the Teichmuller metric. Okay, so either one of those gives you a hierarchy hyperbolic space. 5 pi1 of any 3 manifold with no nil or sol component. Okay, so you get lots of 3 manifold theory kind of fits inside this. 6, right, so somehow an example that we sadly did not put into our paper, but I realized on the plane trip here we should have listed, which is what Huann calls interpolation, or he introduces interpolation complexes. Okay, so he introduced this sort of interesting family of spaces that interpolate between the curve complex and the mapping class group. We sort of independently in a paper kind of studied these spaces, but I'd forgotten at that point that his paper existed, but I remembered it on the plane right here, so I'll make sure that we sort of mention this again in the future. But these interpolation complexes is sort of an interesting family of examples. And the list goes on, so I'll stop there, but there's plenty of interesting examples there for everyone. There's also then combination theorems and other ways to produce more things. Okay, so let me maybe quickly say a few non-examples. So not everything fits into this context. So non-examples. So out Fn, right? As long as that's not itself free, out Fn is not an example of a hierarchy hyperbolic space. And the reason it's not is because of this more general property too, which is any group with larger than quadratic Dane function. So it was proven that out Fn has larger than quadratic Dane function. So we proved that every hierarchy hyperbolic space has quadratic Dane function, or at most quadratic Dane function. And so that's an obstruction to things like out Fn being an example of one of these. That's right. Yeah, exactly. Yeah, right. Okay, so Huann had asked earlier about thinking about the rank of the space. So let me introduce an interesting family of subsets of one of these spaces, which we call product regions. What about Lie groups? So, yeah, that's right. So I think the answer is that they satisfy this structure, but no one's written that down. So yeah, I've thought several times I should think through the details of this, and I haven't done it yet. But yeah, it's a good example to think about that someone should write down. So product regions. So here are some examples. Let me just start by examples, and then I'll kind of say what the general setup is. So in the mapping class group case, if Y is a subset of S, if Y is a subsurface of S, then the mapping class group of S contains a copy of the mapping class group of Y cross the mapping class group of S minus Y. So at least we get a, I should say maybe, we get a quasi-isometrically embedded copy of the mapping class group of Y cross the mapping class group of S minus Y. Okay, in the Artin group case, so this is the first example, and the second example, if you take some lambda contained, well, let me do it like this. So I'll just do a simple case. So, well, I might as well write it in general. If lambda is contained in gamma, so if you have some subgraph of gamma, then you can take the Artin group on gamma, and that contains a copy of A sub lambda cross A sub link of lambda, where these are all the elements, distance 1 from every element of lambda, from each x in lambda. Okay, so it's just the link, right? You have some, a simple example is you have a point. Right, here's my point, so maybe lambda was this point. Okay, and then we would look at everything that's distance 1 away from that. In this case, these 2 points, and we know that distance 1 corresponds to commuting, so we get a direct product of lambda with this link of lambda. Okay, and so those are the 2 examples. So in the general setup, right, so in a general hierarchy hyperbolic space X, what do you do? So you pick some element, you pick Y, so let's let U be in script S. Okay, so then what we do is then what I'll call the product region associated to U is a direct product of, so it's a direct product of 2 sets, right? So it's a direct product, let me say this, a direct product of simpler hierarchy hyperbolic spaces. And the right way to think about what those hierarchy hyperbolic spaces are is, so let me say, with the property that all distance formula terms between points in P sub U are either from Y in S with Y nested inside U, or with Y orthogonal to U. Okay, so in these 2 examples, what does that mean? Right, in the mapping class group, here we have this subsurface Y. How can you accumulate distance between 2 points in here? Either the distance is happening in this mapping class group of Y, which means that right, if both points were in this particular region, then all your distances are contained inside Y. Or if you have distance between points, some point here and some point here, maybe you need to move a little bit inside U, and then you're moving in here, and these things are all orthogonal to U. So, right, so these things are all disjoint from U. So in other words, you don't get any distance formula terms that overlap U. Everything is either nested inside it, or it's orthogonal to it. Okay, and you can verify that that's what goes on in these 2 examples. So this is kind of a general setup where you can look at these general forms of products. Okay, and these are, right, these products are quasi-asymmetrically embedded inside X. Okay, so what I want to do now is return to thinking about quasi-flats. And I want to tell you about maybe two relevant, a couple relevant examples. So here's some results on quasi-flats. So before I get to the relevant theorem, let me just make a couple remarks. So remark one. So we started by saying there was this motivating theorem of what happens in the case of symmetric spaces, where it was you had an arbitrary quasi-flat and you wanted to prove that it was uniformly close to standard flats. Now, when you go into the world of finitely generated groups, there's no notion of standard flats because there's no, like, everything is only defined up to quasi-isometry. There's no natural, right? There's no natural isometrically embedded flats. And so even formulating what the right version is of a quasi-flats theorem in the general finitely generated group setting is somewhat complicated. So figuring out the right formulation is always a good start. So a natural guess, so let me make two remarks. So in the mapping class group of S, the first remark is that there exist quasi-flats which are not close. Well, okay, sorry. Let me start with this. So the natural, right? So Dane twist quasi-flats are a natural guess, or a natural family of standard flats. All right, so it's a Dane twist flat. You pick your surface. You just take the maximal number of disjoint simple closed curves possible on that subsurface. Right, for the genus 2 surface, that's 3. You simultaneously Dane twist along everyone. That's a free abelian subgroup of rank the complexity of the surface, in this case of complexity 3. It turns out those are quasi-asymmetrically embedded. I mean, that was known before, but for instance, you can see that directly from the distance formula. And so you might think that those are the right family of flats to think about. So the first comment to make then is that if we take, there's another type of flat that can occur, which is, here I have some separating curve. I can Dane twist along that. That gives me a copy of Z. But then over on either side of this, I could look at some. I'm going to draw it like this. I could put in a pseudo-Anosov. So a pseudo-Anosov. On each one of these ones punctured tori, and a Dane twist here. Dane twist. So this is another type of maximal rank free abelian subgroup, in this case of rank 3. So it's got the same rank as a Dane twist flat, but this is not close, right? So this is not close to any union, right, to any finite union of standard flats, of Dane twist flats. Okay, so we need something a little more. So this is not. These are interesting flats, but they're not. These aren't the right definition of standard flats. Another example, maybe another example. I should also say. Here's another remark, which is. So here's my surface S05, the 5-punctured sphere. Here's something interesting that you can do. You could take some simple closed curve, and then, let me call that maybe gamma 1, and then I could take another simple closed curve disjoint from it, gamma 2. Okay, in gamma 1 and gamma 2, here's gamma 1, here's gamma 2. You can independently Dane twist along those. So I could sort of take a positive ray of gamma 1 and a positive ray of gamma 2, and I could get some quadrant here. Okay? But now it turns out that gamma 1 isn't the only curve disjoint from gamma 2. I could take another curve, maybe gamma 3, and gamma 3 intersects gamma 1, so they don't span a Dane twist orthant, but gamma 3 and gamma 2 do. Okay, so far I have this orthant and I have this orthant. And then I can keep going in this way. So I could now take this orange curve gamma 4, which is disjoint from gamma 3, and I could get another orthant down here. And then I could do one more thing, which is find another color. So here's green. I could take, where is this? So I have gamma 3, I have gamma 4. See, I want gamma 5. So gamma 5 now is disjoint from gamma 4. So they span an orthant. Dane twisting along those two things span an orthant. But actually gamma 5 is also disjoint from my original gamma 1. So there's an orthant here too. So this is a nice concrete example. This is a quasi-flat. You can check that this is a quasi-flat. Right? It's 5 orthants glued together along a point in this nice way. This gives a quasi-flat, which is not uniformly close to any single Dane twist flat. It's close to this union of 5 of them, but it's not close to any single Dane twist flat. Okay, so this is not close to a single flat, a single Dane twist flat, but it is close to this union of 5 of them. Okay, so that's also a good example to keep in mind. Right. So let me say a positive statement now. So let me state a theorem that was proved recently by Jinying Huang. There's lots of Huang, so I'll write J H-U-A-N-G. So what did he prove? So he proved a theorem in the context of cat-0 cube complexes. So he proved that X be an n-dimensional cat-0 cube complex. And let capital F be an n-dimensional quasi-flat in X. Okay, so these two things have the same dimension. So the dimension of this cat-0 cube complex and the dimension of this quasi-flat coincide for his theorem. Okay, so if you're in that setting, he proved, then there exists there exists cubical orthants, right? By which I just mean, right? So there exist cubical orthants, O1 to OK. Right? So a cubical orthant is just 0 to infinity raised to the power n with a standard cubulation. Okay, so there exists some finite collection of cubical orthants for which the Hausdorff dimension of F and the union from I equals 1 to k of these orthants is bounded. Okay, so he proved a quasi-flats theorem in this context of cat-0 cube complexes where the maximal rank of a quasi-flat coincides with the maximal dimension with the dimension of your space. So this is an interesting example. It covers lots of cases that weren't previously done. So this generalized, the two-dimensional case of this was proved like 10 years ago by Besvina, Kleiner, and Segev. So they did this in 2 dimensions. So he generalized it to n dimensions. This covers many cases. For instance, it covers all right-angled Artin groups. For right-angled Artin groups, the dimension of the cube complex coincides with the dimension of the quasi-flat. But it doesn't cover, not in covered cases. So some cases not covered are if you just took this very simple cube complex that looks like the line and you put in one two-dimensional cube, then this no longer works because the dimension of the cube complex doesn't equal to the quasi-flat rank. So this has a two-dimensional cube complex but a one-dimensional quasi-flat rank. So that's sort of a stupid example that's not covered. But right-angled Coxeter groups are also not covered. And to see that, right, if you just took the hyperbolic plane, if you took a surface and you cubulate your surface, that gives you a cubulation of the hyperbolic plane. There's a two-dimensional complex, but the quasi-flat rank there is 1. So this is this is a useful theorem, but it's it has a limit, which is that you need to know that the quasi-flat rank is exactly equal to the flat rank. Okay, so let me now state what our theorem is. So our theorem actually ends up relies on his theorem, but it generalizes it. So let me first say what our standard flats are. So I told you what the product regions are. So what we consider a standard flat is the following thing. So orthents in hierarchically hyperbolic spaces are defined in the following way. So if U1 to UN are all elements of my index set and are pairwise orthogonal, so you think about a collection of disjoint subsurfaces, and notice that a collection of disjoint subsurfaces might be these 3 Dane twists, or it might also be these 2 once punctured tori in this one boundary, in this one annulus, or neighborhood of an annulus. Okay, so it could be either one of those cases. Then a standard orthent is a product of hierarchy rays one in each factor. Okay, so associated to this U1, right, there's all the elements in my space where all the distance is contained inside U1. So that turns out to give me something like the stabilizer of Y. We can do that in this general setting. So you look at all the elements that are contained inside this domain, and then each one of the domains simultaneously. In each one of those, you just take a product. So in the 2 examples we did, if U was equal to if we had U1 was the annulus around this curve, and U2 was the annulus around this curve, and U3 was that annulus, then a hierarchy ray, well, there's only one, right? All we could do inside the annulus is just Dane twist. So I'd have a product of 3 Dane twist. On the other hand, if over here I had U1 was this blue surface, and U2 was this annulus around this curve, and U3 was over here, then I could take an arbitrary geodesic in this mapping class, in the mapping class group of this U1, right? So that's a copy of right? It's quasi-asymmetric to a free group, it's virtually free, and this is virtually free, and this is a copy of Z. So any kind of product of one of those 3 geodesics, as long as it behaves nicely inside every subsurface. Okay, so those are my standard orthents. Yeah. They project nicely into every into every element of the index set, with a hyperbolic space associated to every element in the index set. Okay, and so now let's set nu, which depends on x, to be the max rank of a standard orthent in X. Okay, so inside your space, you look at all the standard orthents and you write down the maximal maximum rank of one of those. Okay, so this is what Mohali asked about earlier. Okay, so now we can formulate the theorem. So the theorem is the following. So, let X be a hierarchy hyperbolic space with, well, I didn't give it a name, but okay. So let X be a hierarchy hyperbolic space if F is a new dimensional quasi-flat in X. So if it's a top dimensional quasi-flat inside X, then there exists standard orthants O1 to OK such that such that the Hausdorff distance between F and the union from I equals 1 to K of these OIs is uniformly bounded, is bounded. Okay, so not just is it contained inside a finite union of orthants, but it's actually it's Hausdorff close. The K is dependent on the quasi-isometry constants of the flat. That's right. Yeah. Yes. So once you fix the constants, you get some uniform bound on what the number is, though. Okay. So a couple things. So one is right. So what are some applications of this? One is that over here you had to have the dimension of the quasi-flat equal to the dimension of the space. Over here, I just need the dimension of the quasi-flat to be the maximal dimension possible inside that. So there's no restriction in the CAD0 context of, there's no restriction in the CAD0 context of what the dimension is of the ambient space. So one corollary, right, was a sort of this folk conjecture that the quasi-flats theorem holds for all cubical groups. Okay, sorry about that. So this holds for all cubical groups. There's a quasi-flats theorem. That's one corollary. Another corollary was this conjecture I mentioned at the beginning. So this Farb conjecture. Right, so MCG of S satisfies the quasi-flats theorem. I'll just write QF theorem. Okay, so we get a quasi-flats theorem for the mapping class group. Another corollary, right, is a Jeff Brock had asked a question about whether this held in the Weil-Petersen metric. So WP satisfies the quasi-flats theorem. So there's kind of, and the list goes on. So there was kind of all these outstanding conjectures in sort of different areas, and we were able to kind of prove all of them simultaneously with this sort of one general framework. So I think this is a useful setup for doing things. So I guess in the last few minutes, I thought I would maybe give, I thought I'd maybe mention sort of one of the tools that shows up, which I think is a useful tool to think about. So here's one of the ingredients in the proof. So maybe I'll just talk about one ingredient in the proof. So one thing that's useful is that in this context, we have a nice way to build convex holes. And so there's a nice way to build convex holes, and one of the one of the key ideas involved in proving this theorem is proving that there's these convex holes in hierarchical hyperbolic spaces, and they have good approximations by cat-zero cube complexes. And it turns out that that's sort of it turns out to be very non-trivial, because even in the case of a cat-zero cube complex, we get so we end up proving something like that, and then we use, in the end, Huang's theorem. So what happens is, even if you started with some cat-zero cube complex, turns out we can give an approximation that's better than the standard kind of cubical convexity. So we get some kind of very kind of thin, small subset, convex hole that contains sort of a finite set of points, and that one has a much lower dimension than what the ambient space is. So the convex holes we build are going to have kind of a small dimension in the sense of these sort of standard orthants, and therefore, by kind of even in a cat-zero cube complex, you'll be able to take this approximation and then apply Huang's theorem to this in some limit. So let me tell you how we build these convex holes. So convex holes. Okay, so here's the idea. Consider a finite set. A contained inside X. So we want to have some way of describing sort of what are all the points that are between them. So here's the definition. So here's the set. It's the set of X in my space that have the following properties. So where do all these kind of delta hyperbolic spaces come in? So this is exactly where. So this is the set of all X and X such that the distance in C of U between X and the hole inside C of U of A is bounded by something. So is less than or equal to K for each U in script S. Okay, so there's a lot of notation there, so let me help you parse this. So this is, so I'll call this the whole sub K of A. All right, so what does this mean? So I've got some points sitting inside my space X, and what do I want to do? I want to, right, so X comes as part of the package with a bunch of projections to curve complexes. So I can project, so here's A, maybe I'll call it A1, A2, A3. I can take any triple and I can project, or any set that I have, let's say it's a triple, and I can project it into the curve complex of U for any possible U. Now, what's nice in U is that U is delta hyperbolic. Okay, so there's a well-defined convex hole inside a hyperbolic space, and it's coarsely a tree. Okay, so inside any one of these hyperbolic spaces, the projection of these 3 points is coarsely a tree. And so what we want to do then is we want to define a point to be in the convex hole. Right? This is a subset of X. Inside X, we want to define all the points so that when you project to every curve complex of U, you can you're inside the associated tree. Okay, so what does that get us? So that gets us, okay, so a priori, right, this gives us, so we can look at all these projections, and then we get some this gives us some vector, right, we think of as some point inside this infinite product of curve complexes of U. And this is where we use, right, this property that I talked about a little bit for mapping class groups and a little bit for cat-zero cube complexes, that there's some kind of realization theorem, that if you have a point inside the infinite product of all these curve complexes, then it comes from a point inside X if and only if it satisfies certain local consistency conditions. And so what we do is that we consider these projections, and then we verify that these things all satisfy some sort of local consistency conditions, so that we can then pull them back and get some elements inside X. So this this space is necessarily non-empty because it contains all the, it contains all the A's, but it turns out it gives you this nice subset. It gives you a nice subset of X. What? So if you're in a group, then these are uniformly hyperbolic. Yeah. So after pulling back, it's not hyperbolic. So this is not. So this is not hyperbolic. This may contain big flats in it, but part of what we prove is that. So let me write this. Let me write just the theorem about this. So it definitely may not be hyperbolic, because if you started with, for instance, if you started with the mapping class group and you took 3 points inside a Dayton twist flat, then you would get sort of you might get a subset of a cube inside that Dayton twist flat. Okay. On the other hand, we prove the following. So, A is a finite set inside some hyperbolic space X. Then, so there's constants here. It turns out that everything works as long as the constants are big enough. So then I'll just write H of A, the convex hull of A for some large enough set of constants, is quasi-isometric to a cube complex, to a cat0 cube complex of dimension less than or equal to this quasi-flat dimension, right? This maximal dimension of one of these standard orthants. So we end up getting a approximation by a cat0 cube complex, where that cat0 cube complex may have much lower dimension than the ambient space. So even if you start with a cube complex, you get a space where the bound is what you get inside a is what you get from the rank. So if you started with a cubulation of hyperbolic plane and you take 3 points, you'll get a quasi-tree. You'll get something that's hyperbolic. If you take something that's higher dimensional, if you get something with higher dimensional orthants, you may get something that's higher dimensional, but you get a nice uniform bound on what the dimension is. Okay, and these and the various constants here depend only on the space X. Okay, so this is sort of the approximation theorem we get, and then the general idea is that we get these nice approximations, and we end up kind of approximating larger and larger subsets of the quasi-flat, and eventually invoking Huang's theorem, even though it's in an a priori weaker statement. But because of the fact that we now get spaces where the quasi-flat dimension is equal to the dimension of the cube complex, you can apply his theorem on the nose. Okay, so maybe that is a good place for me to stop, and thank you for listening.